In this lecture, we are going to see the solutions of the questions which you have tried on your own in the last lecture. Remember that there are few exams which allow the use of virtual calculator. So, you should be familiar with virtual calculator. By solving these questions, you should use virtual calculator. For the first question, we have to find the ratio of thermal voltage at 50 Fahrenheit to 50 degrees Celsius. First, we will convert both the temperatures in the same scale. I am going to convert Fahrenheit into degrees Celsius. We have the formula for converting Fahrenheit into degrees Celsius, which is converting 50 Fahrenheit into degrees Celsius. We will get 10 degrees Celsius. Now we have to find the ratio of thermal voltage at 10 degrees Celsius to thermal voltage at 50 degrees Celsius. And we know thermal voltage is equal to kT divided by Q. K and Q will cancel, which will give T1 upon T2. And you should know that temperature in thermal voltage is always taken in Kelvin. Therefore, we have to convert this temperature which is present in degrees Celsius into Kelvin. So, we will get 283 divided by 323. The ratio will come out to be approximately 0.876. We know that energy band gap is equal to E1 minus E2, and from the graph we can calculate it, and we will find the band gap to be equal to 3 electron volt. Also, change in kinetic energy of the electron from conduction band to valence band can be found as J plus E minus J. Therefore, change in kinetic energy is equal to E. It is also provided the energy of quasi-particles is equal to Ex and Ey. Now, for the first part, first you have to understand that suppose that we have a photon which is striking the electron like this, and this photon energy is completely dissipated into 4 components. First part of energy is used in overcoming the energy band gap. Second part is used in the change in kinetic energy. And the third and the fourth part are used in providing energies to the 2 quasi-particles. Therefore, we can write photon energy to be equal to Ex plus Ey plus change in kinetic energy plus band gap energy. We can write photon energy to be equal to E plus Ex plus Ey plus Eg. The value of E plus Ex plus Ey is provided in the question to be equal to 2.8 electron volt, and we found the band gap energy to be equal to 3 electron volt. Therefore, photon energy is equal to after calculating, you will find the photon energy to be equal to 5.8 electron volt. Now for the second part, it is given that the photon energy is 6 electron volt. Then we have to find the quasi-particle energy Ex. From the first part, we can write 6 is equal to Eg plus E plus Ex plus Ey. And we know the value of band gap energy is 3 electron volt. Therefore, we can write E plus Ex plus Ey to be equal to 3 electron volt. In the question, it is provided that ratio of E to Ex to Ey is given as 3:5:6. Let us assume that E is equal to 3x. Therefore, Ex will be equal to 5x and Ey will be equal to 6x. Now putting the values of E, Ex and Ey in the equation, we will get therefore the value of x comes out to be 3/14. Now we have to find the value of Ex, which is equal to 5x. We just found the value of x to be equal to 3/14. Therefore, the value of Ex is equal to 15/14 electron volt, which is approximately equal to 1.071 electron volt. We know for silicon we have the band gap energy relation like this. Similarly, for germanium we have energy band relation like this. Now, to find equal energy band gap, we simply have to equate these two equations. After calculating this expression, we will find the value of temperature to be approximately equal to 3102 Kelvin. Let us assume that band gap energy can be written as. Now, it is also provided that at T is equal to 100 Kelvin, band gap energy is equal to 1.2 electron volt, and it is also provided that the rate of change of energy band gap with respect to temperature is equal to 2.37 multiplied by 10 raised to the power minus 2 electron volt per Kelvin. We can write 1.2 equal to A. We have to put the value of T equal to 100 Kelvin. Let this equation be first. We have taken the band gap relation as A T square plus BT plus C, and differentiating it with respect to temperature, we will get 2AT plus B. Now, after putting the value of T equal to 100, we will find another relation which will be like this. Let this equation be second. It is also provided that at T is equal to 200 Kelvin, band gap energy is equal to 4.74 electron volt. Again, putting the value of T equal to 200 in the original equation of band gap energy, we will find another relation which will be like this. Let this equation be the third equation. Now, we will subtract the first equation from the third equation, which will give Let this equation be the fourth equation. Now we will subtract 100 times of second equation from the fourth equation. By solving this expression, we have found the value of A to be equal to 1.17 into 10 raised to the power minus 4 electron volt per Kelvin square. Now we will put the value of A in the second equation. By solving this expression, we will find the value of B to be equal to 3 into 10 raised to the power minus 4 electron volt per Kelvin. Now, putting the value of A and B in the first equation, we can find the value of C. After calculation, you will find that the value of C comes out to be 0. Therefore, the function of bandgap energy with temperature comes out to be like this. This is our final answer. State whether the given statement is true or false. The energy band gap is inversely proportional to temperature. For reference, we are going to take the energy band gap relation of silicon. We can see that as the temperature increases, band gap energy decreases. But it does not mean that the energy band gap is inversely proportional to temperature. Because if we say that the energy band gap is inversely proportional to temperature, then energy band gap multiplied by temperature should give a constant, which is not true. Therefore, this statement is false. It is true that if the temperature is increased, band gap energy will decrease, but still, band gap energy is not inversely proportional to temperature.